Thank you, Pauline, for this nice introduction. Actually, it's my great pleasure to be here, and in particular to introduce Professor Nick Terrill. He works in an area I'm very much interested in and very active in, and actually we hope he can actually help us solve one of the outstanding issues in the next generation of solar cells, which are based on plastic. So these are third-generation solar cells. But the problem is they're based on plastics, polymers, and they're complicated structures. They're based on long chain of molecules, like spaghettis. And in these solar cells, we put another material in, a fullerene, like a hockey ball, so like a small football, but on a molecular scale, which actually can transport electrons. That's very important. The problem we have is we can get now very efficient solar cells, and I know Professor Terrill will talk about it, but we still don't know exactly what type of microstructure we have, because these polymers have very ordered structures, but they're also in parts really like cooked spaghettis, very unordered, where the hockey balls, these little footballs, sit in. And we really have to learn which of those phases, these ordered or these unordered phases, are important. And there's actually evidence that's not only the ordered phases, let's say in silicon solar cells, it's very important to order these silicon atoms very accurately. In the polymers, it seems we need ordered type of structures, but we really need these unordered phases. So therefore, work which is done at the beamline will hopefully help us, because plastics usually don't diffract a lot. We will hear about diffraction, so we need these high-intensity beams. So I'm very curious, and it's really, again, a great pleasure to listen now to the talk by Professor Nick Terrill on harnessing the light. Fantastic.
Okay, thanks, Natalie. Good evening. I hope that's given you a great introduction. There's some things I don't need to say now. It's wonderful. The overhead that you've got here is basically a view of the construction phase for Diamond, which is the UK synchrotron. I'm going to tell you a little bit about what that is in a minute. That sort of process took place between about 2002, 2003, and when we took our first users in 2007. It's quite a significant setup. So, my title, and I apologise to Terry Pratchett, but I'm afraid I do read some of his books. Harnessing the Light, Fantastic. I'm going to try and tell you how we harness the power of the synchrotron, the diamond light source, to actually look at some things which are intrinsically interesting to us, but also could really help with one of our major problems, energy generation. And safe, clean energy generation is going to be something that becomes more and more important as we go through the next few decades. So I'm a principal scientist at Diamond. I've built one or two beamlines now, and what I'm hoping to do with those is actually do some of this interesting science. So over the next half an hour, three-quarters of an hour, I'll try and do a little bit of telling you what we do. So this is the Harwell campus, and the synchrotron that I'm talking about is this thing here at the front. But Harwell itself is a brilliant place to work. It's not only the synchrotron, we also have the UK's neutron facility there. We have high-power lasers here. We have space science people working in microstructure. And it's all of these sort of people coming together that we're hoping will actually start to sort of solve some of these big problems that we've got. And one of the most recent additions is a research complex at Harwell, where we're actually having visiting scientists come and not spend a few weeks with us, which is what they do when they do the experiments, but actually spend several months or even several years on site working with local scientists, trying to actually get the experiment right, and you'll see a bit of that later, so to actually get the answer right. If you don't get the experiment right, you're never going to find out how to find the answers we want. So, what is Diamond? Well, it's been coined a number of ways. It's certainly a very intense source of light. A series of super microscopes is one description. This one actually, I think, is from the Mail. But it could be considered an X-ray machine, but it's more than an X-ray machine as well. So I naively like to think about it as a scientific torch. It's a very powerful torch, but nonetheless it's actually used for actually shining light on things and getting information about what those systems are like in a range of different ways. We like to think it's a world-class facility, and we're starting to build up a whole gamut of science that is actually world-renowned, and we've got experts in various fields at the facility doing that. And it's actually a vital tool for UK science. We have at least 2,000 user groups coming to use us on an annual basis. Over the next few years, that's going to go up even further. So it's a major contributor to certainly the academic side, but now more increasingly also the industrial side of the UK. We have industrial chemists come and actually use the facility on a fairly regular basis now. To give you an idea of what was inside that donut, if you like, these are just some construction photographs. So this is our actual storage ring. I'll tell you a little bit more what those are. Our linear accelerator, and at the beginning of this is an electron gun. I used to talk about television sets. Doesn't really work very well anymore because there aren't very many cathode ray tubes around anymore. But in the old television sets, and some of you will remember them because I do, they were about this big. Ours is slightly bigger than that. But it's still basically an electron generator. That's what it's there for. It generates a bunch of electrons which then get accelerated down into what is a partially built booster synchrotron. That won't work. And then into the storage ring. And this is one of the girders of the storage ring. So it's a massive undertaking. You can see that's actually getting on for 20 tons of kit. And we've got 72 of those just to move in. So, what I mean by a cathode ray tube, well, I've actually got one here. I'm supposed to be able to just turn it on. And hopefully some of you can see that there's a blue line here. That's basically the interaction of the electrons we're generating from the cathode tube. And they're travelling in a nice straight line until I bring a magnet into play. Now, we have over 100 magnets in the synchrotron. Every single one of them is controlled a little bit more accurately than I'm doing it now. But basically actually allows the electrons to go around our storage ring. So we have magnets that just do that bit. Then we have magnets which actually generate waves in the electrons. And quite often now for most of the science that we do, those electron waves are where we actually generate the very intense beams that we use on the experiments. So just a simple example of a cathode ray tube and the fact that you can actually move electrons around with magnets. And go back to the talk, hopefully. So we've taken the top off now, if you like. And our LINAC, or our linear accelerator, is in this bit of the building. The electrons are generated, brought into our booster ring, where they are speeded up. And our electrons, by the time they've left the booster ring, are 99.99, a few nines, the speed of light. They're not quite at the speed of light, because that's impossible for us, but they're very close. What that allows them to have is an awful lot of energy. As they're going around the storage ring, the magnets that we have in them, some of them are bending magnets, some of them what we call insertion devices, wigglers and undulators. Physicists are really imaginative. Wigglers wiggle the beam up and down quite a bit. Undulators gently undulate the beam. That's all they need to do. The wiggler is basically a brighter version, annoy some physics people, a brighter version of the bending magnet. So there's just more power, but it's a big beam. The undulators, which we tend to use for lots of our experiments now, are a much more collimated beam, if you like, a much finer beam. We can do lots of new things with that. Once it's come out of the booster, the electrons circulate in that storage ring, and they generate light. And this is why I don't like the definition of an X-ray instrument. Diamond actually generates light all the way from infrared to hard X-rays. So we actually have instruments there now that will actually utilise that light for a whole range of science. We have an infrared beamline that's actually looking at cells, actually trying to diagnose early markers for cancer and in individual cells, so actually mapping an individual cell with it. We have UV beamlines looking at, just the other side, UV beamlines looking at proteins in solution before they've been crystallised, just to get some idea of how the protein is organised. And then into the hard X-rays. And don't get me wrong, we do use the X-rays quite a lot. It's a modular design. That was the bits we saw earlier. This is for the people who like numbers. It's 561.6 metres round our synchrotron. It's the fourth largest around. There was one built at the SRF in Grenoble, which is the European synchrotron. That was a 6 GeV machine. That's a decent size. The Americans then built one at the APS in Chicago. That's a 7 GeV machine. That's a bit bigger. And then the Japanese decided, no, that's not good enough. We'll build an 8 GeV machine. They've actually got a small mountain on the inside of theirs. So it's a bit bigger. It's still not the same size as the CERN facility, but certainly large facilities for doing science. It's not actually a circle. It's actually a 48-sided polygon, which is a tetracontachi octagon. I had to learn that this week. It's actually lots of straight sections joined together with our bending magnets, in fact. And it's in the straight sections we do most of the science now. 22 of which, in this case, we can actually use for science. The others, one is to get the electrons in, and one is to give them a kick every time they go round. They actually get some radio frequency energy to keep the electrons going round in our storage room. And then a series of magnets that actually allow us to move things around. Diamond itself started off as 7 beamlines in 2007. We've already built most of the next phase. 19 of those are now in operation. We've got 3 in various stages of commissioning. And we've already had funding even in this environment for another 10. So that's actually going to take us to 32 facilities, the first few of which will already be up and running in next year. So they've certainly sort of invested in this, both previous government and the current government. But when I talk about how bright we are, let's start with something really simple. That's a candle. We'll take it as 1. Otherwise, we have to start, even for a candle, we have to start adding quite a few noughts. So you go from a candle to a light bulb, you go to 10. So it's an order of magnitude. Anybody know what this is? Yeah, for schools, this is quite a good one, because what on earth? It's blue. What is it? It's actually a UV picture of this, which is our sun. And if you compare that with the light bulbs, you're going up to 100,000. So already you've gone quite a long way up in scale. So, how bright do we think diamond is? Well, I'll start it bringing in. Diamond's a very bright source. It's about 10 billion times brighter than the sun is. And then people looking, what? How? Our beams are so small. The amount of electrons we've got, when you talk about brightness, it's photons per unit area, per unit volume, or angle, if you like. So we probably don't generate quite as many photons as the sun, but certainly in brilliance terms, or brightness terms, it's a very bright source, and it's that allows us to do the science. So now I need to step back. We've probably all seen this sort of thing. A number of us, unfortunately, have had hospital x-rays. This was probably one of the very first x-rays ever taken, and us scientists were very cautious. This is the guy that got the Nobel Prize for various things, including x-rays. But he didn't actually, if you notice, x-ray his own hand. He let his wife put her hand in the beam and took an image of that, and that's the wedding ring that you can see. And you can see that sort of just from absorption, you're starting to see the harder tissue. That's just an absorption pattern. That's one way of utilising x-rays. But it's certainly the start. Our x-ray beams do a whole lot more than that. We do some absorption. It's in this sort of experiment here, but we now tend to tailor the x-rays that we use so that we can actually pick out various chemicals. Different elements have a different response to a particular wavelength or energy of x-rays, and you can actually map out where those elements are. So that's absorbance and fluorescence, in fact. That's the same sort of idea. We've got diffraction and scattering. Those, if you've done anything sort of towards looking at how atoms are put together, those are the techniques that you'll be using to actually see how the atomic structures are put together. And then the other way we actually also use quite often is actually using our x-rays to knock things out. And this is sort of photoemission electrons. And that's a really useful technique for surface science, trying to really understand how surfaces are put together on a semi-atomic level. Okay, so one of the things that I said we can do, Dave wants to turn the lights down a little, is we can shine light or x-rays into something and hope to get some information out of it. So here's one I created earlier. Here's a series of spots. It's just in a line. From those, the fact that it's just a series of dots on a line, I can tell that what's on this is actually a series of lines. Now, that's a really simple example. Let's try something that's slightly more complicated. This And it's actually in the important bit really is in the detail. It's not so much in the cross, it's in the spots that are what we call off-axis. The fact that they're off-axis, we can actually measure where they are and very accurately tell that what this pattern is actually a herringbone. So if you've seen parquet flooring, this is a very small version of that. And you can go through all sorts of different shapes and sizes. And one that I like quite a lot is this one, if I get it right. Now, it's not perfect, but I do quite a bit of very amateur astronomy. And that's actually a star. So lots and lots of little stars, and the dots actually make up the pattern. So basically the idea is you shine light into something, and from its structure, it does something to the wavelengths of light. Exactly the same with diffraction and scattering. If you shine X-rays into things, because the length scales are right, you can actually get information. And this is one we prepared earlier. This is actually off one of our MX beamlines, our macromolecular crystallography beams. So actually looking at proteins or macromolecules. And each one of the dots tells the scientist something about where the atoms are and how they're arranged in the protein. That's really, really beautiful, really easy. But then you can actually do it for all this sort of stuff as well. And everything on that montage is something that either has been to Diamond already, not necessarily in the full car, but parts of it. And definitely not the planet Saturn, but we can actually recreate things there. But everything here, we've actually looked at one way or another at the synchrotron, so you can see the breadth of science that we actually do. I'm not going to talk about all of them today, that's for sure. This is a beautiful tapestry. This is actually probably not far off the size it actually is. And David Godsell's done this. It actually shows sort of areas where bacterium are. So this is the interface between the bacteria and its surroundings. And all of these little different shapes and sizes are various proteins that the protein crystallographers or the macromolecular crystallographers now are really interested in trying to understand form and function of all of them. And just one for the men. I'm sorry, we are wetter than women. It's fact. So one of the things we do a lot of at Diamond, and we've got several beamlines for doing it, is solving protein structures, either solving the protein structure itself or solving a structure of something that's akin to a protein with a drug attached. And there's an awful lot of drug development work that's actually done by doing protein crystallography. But first, you've got to grow your crystals. And that's not trivial, as anybody who's tried will know. These are actually rather pretty ones. They'd be delighted if they got something like that. Then you get your pattern, another pretty pattern to show you. It's always a good excuse. And then ultimately you get a structure from it. And what they're interested in this case is actually a drug to do with HIV. And it's actually looking at a drug design, so how the drug actually fits into the protein and how it actually would stop HIV from actually sort of carrying on its growth process. It's actually an interference process. But if you don't know where it's going, you can't actually design the drug properly. And that's the whole idea of this kind of technique. Other things we do, and I'll whistle through some of these. This is the absorption or fluorescence measurements. I was talking about being able to do things with chemical speciation. We've had groups from the Mary Rose Trust and the University of Kent come to us with samples from the ship and trying to understand how the wood is decaying, if you like. A lot of it is down to sort of sulfate and sulfur materials actually inside the wood eating away at the system. And that's come from the old nails. So they're now trying to figure out, because they understand what the process is, how to actually sort of prevent that from making it even worse and then preserve the Mary Rose for future generations. We've had a small role to play in that. I put Saturn up there for a reason. Because of all of the intense light that we can use, we can start developing cells and systems that you wouldn't actually be able to use maybe in your home lab. And we can actually recreate the conditions, both pressure and temperature, that they would actually have in these gas giants, in things like a diamond anvil cell, and start to actually understand some of the sort of geochemistry of these sort of bodies in space. That was very much a whistle-stop of things I'm not going to talk about too much, but it gives you a flavour of what Diamond's about. My technique, if you like, is scattering. And this is a scattering experiment. Just so happens that this is the moon. And what we're scattering are actually ice crystals in the upper atmosphere. With a bit of knowledge of knowing how far away the moon is to the upper atmosphere and then to the observer, I could work out and tell you how big those crystals were. Not going to, but I could. I could also actually tell you what shape they were to some extent. And they're just randomly organised in the upper atmosphere, like water droplets, only frozen out. So that's what the principle is. We obviously don't do it with light, that's a light experiment, but this is with X-rays. And the scattering intensity is still there as long as the length scale's right. Turns out polymers are perfect for this sort of scattering technique. They have length scales above the atomic length scale, which are really, really interesting. But they don't necessarily form hard crystalline structures all the time. But we can still get useful information out. So, this is where we need the lights down. I might need some help to hold a torch. If Laura can come up and give you a hand. What we're going to do is prove to you, I hope, with our very intense light source. We lost the big one. This is basically sunlight. It'll hopefully do exactly the same experiment that we were doing before. And instead of with ice crystals, I can't really keep ice crystals cold in this environment. So we're going to put some milk in here. Please work. We've tried this a lot at home, and it's sort of... My daughter loves it. It's great fun. Now, hopefully the lights are low enough that some of you at least, can see that at this end the light is a little bit bluer, and at this end the light is a bit yellow. If you come down to this end, it's starting to go quite orange. I don't think we've got enough milk. I think we'll put a bit more milk in. And actually, all we're doing is recreating what happens every day around us. This is literally why the sky is blue most of the time, and why at sunsets it starts to go orange and then red. And what you're doing is you're actually separating out the different wavelengths of the light that's coming to us from the sun. It's Rayleigh scattering, it's all it actually is. It's not as good as it could be, is it? But
kind of blue and kind of orange.
It's kind of blue and kind of orange, this end? It's almost a nice sunset, which we had earlier on today. Thanks, Laura. Sorry. What that was basically saying, number one, if you have a range of wavelengths, you can separate them out into the colours, and there's more of that. There's a reason why I've done that one. There's actually a polymer reason why I've done that. You can separate things out. But the converse is also true. If you actually start with one wavelength of light, you can actually then start to tell what the size of the thing is that's scattering it. So it's a demonstration of what we do in scattering. If we do it with X-rays, we get an intensity out, and that intensity is proportional to a number of things, some of which we can work out fairly accurate, and some of which are a little bit harder. So there's the number density of the material. That's how many of these things there are there. What the volume of each particle is that's there. This bit is to do with what the difference is between how it scatters and how the matrix scatters. So in that case, it's what's the difference between how the milk fats scatter and how the water scatters. In terms for us, it's usually what we call an electron density difference. So if something's got a high electron density, it will scatter more maybe than something with a low, and you'll get an interface there that you can get scattering from. First function is what we call form factor. It's basically the shape. It's a complicated name for shape. So number one, we can actually get the shape out of a system. And then this extra one is the structure factor, or it's the sort of the lattice component. Now, if you make this really dilute, and that's not a dilute solution, that's now a concentrated solution. If you had one tiny drop of milk in there, that might be considered a dilute solution, but you probably have to dilute that 4 or 5 times, or maybe even 4 or 5-fold, before you get down to what we would consider dilute. If you get down there, you can actually get the actual shape of that polymer, or that protein, or whatever colloid system you've got in there. And that's a really valuable tool for the scientist. It's in length scales that are really relevant to the systems we're interested in. I've put that in angstroms. If you're metric, that's 1 nanometer to 100 nanometers. We've got to go SI, so I'm really trying to change the slides, but I like angstroms. Diffraction, which is the classic stuff that you saw from Bragg, would be down here. And once you start up into this, you're into light microscopy. being able to physically see things down a microscope lens, but sometimes they can be opaque, and there's still a role for both us as the X-ray facility, but also the neutron facility to get inside things that you can't actually shine a light into and still get information about them. So, block copolymers. You heard about the spaghetti, which is a great analogy. When you start off with teaching about polymers, you start off with saying, well, it's sort of like strands of spaghetti and they're stuck together. And if you heat them up, those strands can start to move around a bit easier. And when you cool it down, it goes back to a big lump. You know, the sort of lump you can never get rid of out of the saucepan. Well, that's exactly what polymers do when they get heated up and cooled back down again. But what we want to be able to do as scientists is actually control that process, so it's not a random process to us. It's one that we can actually have some influence over. But if you're going to have some influence over it and they're going to grow interesting structures, you can't have just a simple polymer. It can't just be lots and lots of carbon, which is what most of them are with hydrogen sticking off the end. You actually need to put some chemistry thought in. And we're now at the stage where we can actually grow a whole range of what we call block copolymers. Green bit, red bit. Green bit usually could be, say, something that won't crystallize. The red bit will. Now, if you don't put them chemically together by putting a chemical bond here, they just, what we call macrophase separate. And that's exactly what happens to your oil and vinegar dressing. You shake it up, it works for a while, and then gradually it separates out again. That's macrophage separating. These things will microphase separate. They can't get apart completely because they're actually chemically stuck to each other. So they do what they can to minimize their energy. And they will form a whole range of really interesting and useful structures. Starting off with something really simple, these sort of sheets, where basically we'll take the red block as the crystallizable bit, because that's the nice zigzag, and the blue bit is the bit that's just random chain. That's the bowl of spaghetti, and it stays that way regardless of what you do to it. It doesn't want to be anything else. That gives it a bit of flexibility. The crystalline bit gives it a bit of rigidity. Now, if you can tailor both of those, you can actually tailor the sort of the macro scale property of the material. And that's what a lot of these block copolymers have been built for. To give them some stiffness, some strength, but a bit of flexibility as well. And if you change the chemical composition, or you change the constituents, or the temperature, or the pressure, you can change what shape and form they stay in. And some of these are really, really interesting. These two are what we call bicontinuous phases. That means there's two pieces that are interconnected with each other, but not with the other bit, other than the sort of the chemical bond that has to be there. But it's those sort of shapes and structures that are really going to be valuable for the solar cells later on that we're going to talk about. So it's actually getting that chemical structure right in a way that's sort of processable that we're really trying to aim towards. Okay, now that's one thing we can do with them. Those block copolymers, also, if you mix them together in the right ratios and you have the right chemicals, will change colour. Now, the polymer ones are a little bit hard to make, so you're going to have to bear with me with this one. Here we have a liquid polymer, and we're going to put in, I got told that I had these, so I really ought to put them on. I hate putting these on, they make your hands really sticky and sweaty. And seeing it's been provided by Diamond at no great expense, I'll put my safety specs on. You're far enough back, nothing's going to go off bang, don't worry. So what I need to do is put a little bit, I'm being told a little bit, yeah. You show me how often I've done this demonstration. Ooh. Well, there's a little bit. That's not a pigment. It's not a pigmentary change. It's actually a structural change that's giving you the change in colour. So it's not exactly like our polymers. I'll put it against a white background if you like. There's purple. Maybe if you do it against my shirt, perhaps that would. Okay, so we've got a purple colour, and that literally is just by changing the chemical structure of the molecules that are in here. All chemical reactions that are any use. And I got given a challenge which I've completely failed. I can take it back to its original state again. So you've actually, again, not put a new pigment in. You can see these are, and for the audience that aren't with us, they are both colourless solutions. It's a structural change of the chemicals that are actually in there that is causing this colour. It's nothing to do with adding various types of paint pigment to the system. It's literally structure. And that's actually what the block copolymers do. There's no chemical change, because what we actually add, if I can get the next one up, is a blend. We're not even doing this sort of physically now. There we go. A range of sort of materials that, as long as they're actually in the right chemical composition, will form various, in this case, lamellar-type structures. Those come back to our gratings. They're almost effectively a grating. And what they'll do is they'll, knowing the structure, which is the small angle bit, produce the rainbow. Now, the fact that you can actually do that with what are two basically simple chemical systems and just mix them together and blend them and shear them, which is stir them or stretch them or whatever, you can actually produce any colour filter that you want. And that has a whole wide range of applications that sort of are possible now, from packaging that might actually sort of be relevant for if you've done something to a material, it'll stretch, it'll go that colour, so you'll know it's had something done to it. But equally, there's a whole range of sort of photonic systems for filters, for screens, for all sorts of things, and all from basically two relatively simple block copolymers. And you can basically tune virtually anywhere you want. Now, this is the visible spectrum, but the beauty of this system is actually out the other side as well. We can actually also produce an infrared filter and a UV filter with this system, just by changing the composition of the polymer and producing different sort of blocks effectively. Okay. So, colour from structure is what that one is. So it's being able to use the synchrotron to understand what's going on chemically and help the chemist then produce the right system, and in an understandable way rather than in sort of a black box way. But remember me, the sun? Well, the sun generates 100,000 times more light than a candle. That's got to be useful. And of course it is. Nature's been doing it for probably millions of years, and has actually got quite good at it, to be honest. They're almost 100% effective, this thing. This is a light harvesting complex, and this was solved by protein crystallography. So the light harvesting complex is very good, 100%. This is our figure with the best silicon solar cells that are available. We're a little bit way off on being 100% efficient, but not bad. The only trouble is making enough solar cell from silicon is not going to solve the problem. It's too costly. It would take up vast tracts of land. The process is not particularly nice. So can we think about how nature does it and try and actually come up with some chemistry that might actually help us out? Well, the answer is yes, or I wouldn't be talking to you. So this is how photosynthesis works as far as a physicist or a chemist is concerned. Basically, light coming in, we have a light harvesting complex, takes the light in, creates an exciton, and effectively with a cycle here with electrons being moved around and charges being moved around, this is the ATP synthase. This is the bit that gives you the energy. That process works really, really efficiently in plants and other sorts of systems. And it works because the photon coming in, each transfer, until you actually get the primary receptor out, gets easier. It's a simplified process. Can we try and mimic that process somehow? Because this is a problem. If you listen to the news over the last few months, it's quite clear that we can't carry on with all the energy generation we're doing at the moment. It's too polluting. There won't be any more of it. Nuclear is dangerous. Whether you believe that or not, I don't know. So wind power won't be enough. Wave power won't be enough. So there's a whole load of possibilities out there. And actually, to be perfectly honest, the best one is that. It's going to probably outlast most of us. It's got a few billion years to go. And during that time, it generates this much terawatts, 160,000 terawatts, pretty much hitting the surface of the Earth every hour, I think it is. Total global consumption of energy calculated, and I think this is probably, this is 2006, so the numbers aren't quite right anymore, is 18 terawatts. That's how much the human race uses, not in an hour, but in a year. So, in an hour, the sun delivers enough energy for everything that we could want to do as a human race in a whole year, if we could harvest it. And of course, there's always a catch, and it's the harvesting bit that's the problem. So there are potential solutions. These are massive banks and arrays that you could have a big solar cell, silicon solar cell system. It works after a while, but not perfectly. On this map, I've put on 8 dots. Well, actually, that's not entirely fair. A colleague of mine from Cardiff put on 8 dots and worked out that those dots receive enough energy to actually sort of cover all of our needs over the whole globe. Just those 8 dots. And they only actually have to be 8% efficient as a system. They don't even have to get close to photosynthesis to be really useful. So what I was going to do now, if I could remember how to do it again, is very quickly just show you a solar cell which isn't actually silicon. And just even with the lights in here, they've turned it off. I've got to point it this way. And then it shows up. I can actually show you guys now. There's a value of 10 there. If I cover it up, it drops back down. It doesn't drop down completely to 0 because this isn't quite as good an insulator from light as I'd like it to be. But certainly if you put it back up, it works perfectly well. Now this OK is on the really small scale, but this is a DC current working quite happily, just from the light in here. Just imagine what you could do with the solar system. That process is actually fairly straightforward for the chemists to work on now. But we're never going to be able, like we said, we're never really going to generate silicon solar power cells that are really going to do the job properly. But what might be possible is sort of an organic revolution, where you don't actually have to grow big things, you actually print. This is the silly bit. You can actually print organic photovoltaics on a sheet. That's the theory. In practice, a little bit harder than that, and that's why we're still working on it. But in principle, you could actually have a substrate preparation, actually deposit one of the layers, and then a metal deposition to produce the device, and actually just print it out in great long sheets of it. And the polymer scientists are really good at making really big sheets. I've been to some of the sort of plastics factories, and you can have 4, 5, 6 meter wide sheets of polymer being extruded at hundreds of meters a second. So you can actually generate vast quantities of this stuff. Here it is in slightly larger production role. It's not quite the silicon photovoltaics, but certainly we will be able to do it. But it's never going to work until we can get this bit right. And now we come back, if you like, to all those pretty structures that we showed with the block copolymers. What we actually need for a system to work properly is for it to self-assemble into something what we call a sort of a bulk heterogeneous system, or heterojunctions, where you've actually got interactions between the two layers, the bit that can take in the light and the bit that can then transfer and accept the electron. And that's the electrical charge bit. If we can't grow this properly, the whole process becomes really, really inefficient. And it's there that the synchrotron is starting to play a role. This is the chemistry. So this is the exciting, this is the bit that accepts, and this is the bit that's mimicking, if you like, that processing biology and gradually transferring the energy through. So what we do is we actually drop, at the moment, to try and understand the process, not actually in the big plant, but drop solution onto a disc, let it dry into a thin film, then it gets heated, thermal annealing, and then you can grow your device. And I hope this will show you. We've dropped a sort of a piece of the polymer on. The purple coloration that you can see here is the polymer. And it is actually coloured. This isn't actually sort of enhanced. And then gradually over time it dries. That's the process we've got to control. At the moment, we've got a device there that sits in isolation. What we've done is taken that device to the synchrotron. So that movie that you saw a minute ago is right here. We have ellipsometry to give us an idea of how thick the system is. And that's really important because we want to be able to mimic, as it dries, we still actually want the X-rays to be hitting the surface. And we're trying to figure out the best ways of keeping those together at the moment. But if you do that sort of experiment, you get a structural pattern. So we can actually watch the polymer dry and tell something about how the polymer is organising itself. If you can tell how it's organising itself, you can then start changing parameters, humidity, chemical composition, heat, a range of speeds of the drying process. All of those affect what structure you get out at the end. But we can actually do that on a very small scale and try and actually get inside how those polymers are organising and actually get to a system that's a little bit more efficient. So that was a static pattern that was collected. And on I-22, we've been able to actually watch that process in real time. So you're not taking static images at the beginning or at the end. Because of the brilliance of the beamline, you can actually watch the whole process and see how those polymers interact with each other and actually dry and settle out. And then change some parameters and see how it does it this time. And gradually, over time, you get up an understanding of how these materials work and how you can influence that structure and improve the efficiency of the process. And if you do that, you end up with photovoltaic samples at the moment with this sort of process efficiency of 5.54%. And this is with a slightly modified set of polymers than the ones I showed you in the initial example. We started off the project at about 3.8. So we've made progress. The very best, actually, in some other systems, although they're not actually as well easily processable, are higher than these numbers. They're actually up in the 6s and 7s now. They're still not quite high enough to get to something that's really valuable and really useful. Because although we've said 8% is the whole system. If you take it down to a module, there's going to be losses from the module, and they're about 50%. So you need to get to 16% to really get to 8%. But it's sleight of hand. But at 5.54, we're sort of pleased that we've made progress. We certainly understand how the polymer works a lot better now. And it's really more about, if I can get back to it, it's more about the chemistry now. It's more about which combination of these donor and receptors will give us the structure with the most efficient sort of throughput. And that process is an ongoing one which we're involved in with a range of people. And I've got to go all the way back through them again. Right. And I'm actually going to leave it to a colleague to say what you can do with these things. Well, but of course you're not going to be able to hear it because we couldn't get the video working. What he's actually saying, and this is not just for you here in the audience but also you at home, is that if you can make a sheet of polymer, you can actually mould it around anything. Now, actually he's giving an example. If you could put it around a teacup, you literally could put enough around a teacup to probably keep your tea warm for a bit longer. So instead of it going cold, and mine always goes cold, because I never drink it fast enough, you can actually keep it warm. But let's be realistic about this. We don't really want to put it around a teacup, but you only actually have to walk outside and look at the skyscrapers that are basically all glass. If they were coated with a thin, transparent polymer film, they could all generate their own electricity. They could all, potentially, even be net contributors to the national grid. So you can see where this is actually going. It's not about having great generator farms. It could actually be as simple as coating lots and lots of buildings and making a difference. Yes, we probably want to do both. But actually, these systems could well help us out quite a lot down this road of closing that energy gap. All of that work, and I am coming towards the end, is not possible without a host of people. I've probably left a few number off. The drug design work we saw with the HIV was an Imperial group with Stephen Haran, Volkov and Cherepanov. The Mary Rose is the Mary Rose Trust plus Mark Jones from Kent and a range of other people working on that, including people who are working actually at Diamond, like Fred Musselmans, who looks after some of the spectroscopy beamlines. The coloured polymers is work that's going on in Sheffield in collaboration with us, in chemistry and in the Polymer Centre, and also some work from Ali Adewale, who's at Hull. So that range of people are doing a lot of good work in trying to make these polymer systems better, more easily transferable into the right colour, understanding the process a bit more. And then the OPV team is enormous. It was actually a group from Sheffield, Cambridge and Cardiff working on that initially. And Cambridge and Sheffield are ongoing in that work. And it would be remiss of me not to thank everybody at Diamond for all their efforts. There's 400 of us now, at least at Diamond. All of the work that you've seen is a collaboration between us and our users usually. And without them it would be impossible. And I've got a final one. I've got to thank Laura for getting me here and getting the demos up and running as well as they did. So thank you very much for your attention.
So thanks, Nick, for this beautiful overview, what this macro high-intensity light beam can tell us. I'm sure there are questions from the audience about one of the topics. Please, for those who ask questions, stand up and give your affiliation, so for the recording. Are there any questions?
Thank you.
Can you
Just out of interest.
Can you stand up and give your affiliation? Sorry, a name.
My name is Dr. Andrew Surgis. Andrew Surgis.
Hi.
Hi. Just out of interest, the phenomenon whereby the different conformation of structure of material enables the light to be scattered at different wavelengths, and therefore you can have different colours as you were described. Just to add to the point that nature is manifest with all these different colours, where you don't have the traditional absorption and reflection of the light that's not absorbed. In other words,
one classic example of that is butterfly wings.
Indeed, butterfly wings and the beaks of ducks and certain primates and so on, different colours.
Birds actually use it really quite a lot with iridescent feathers as well.
Yes,
They're
indeed.
photonic crystals, effectively.
Yes.
They're a photonic structure, so it's actually using the structure of something to generate colour, rather than, like I said, we're not doing it with pigments. The classic idea of having a colour is there's got to be something there that's a pigment that's that colour.
Indeed.
We're actually doing it with structure.
What was it, just out of interest, the work that has been done on this phenomenon of colour, was it directly as a result of the inspiration from nature, or was it accidentally discovered? Perhaps.
Serendipity and all that. No, I think some of that actually did come from looking at nature and saying, okay, nature's actually doing this with biological polymer systems, because that's what these things are in bird wings and such like. We should be able to mimic it. Now, I don't think they got there straight away, but they're there now. And yes, they have taken, I think, a lot of their inspiration from seeing things in nature.
Indeed, a lot of discoveries are inspired by nature, aren't they?
Yeah, and I think you see that with virtually all the things we do. A lot of the biomaterials things now are coming sort of full circle back into material science. And you're actually seeing the material science now having the tool set, because that was the problem in the past. They could have the ideas, but they didn't have the wonderful tools. Those block copolymers skipped over a slide that was probably 15 years' work, just being able to get from A and B to put them together, and then put them together in really clever shapes. There's a vast amount of science there. But it's only because we've now got those we can actually do the next step, which is actually put them together in useful things.
Thank you.
Jim Williamson from Imperial College. Could you give us a little bit more information about the little experiment with changing the colour of the solutions? For example, you said you were changing the structure, so were you increasing...
Can you hold the microphone closer?
How did you manage to reverse?
Oh, I can never remember biology. It's universal indicator. So you're actually changing the conformation or structure of the bonds of the molecule from one to the other. Because actually all these were, and I'm going to do the wrong thing now by picking them up without the gloves, is sodium hydroxide and HCl. So you're going from alkali to base. So all it is a simple change in conformation of in the universal indicator of phenol what? Phenolphthalein. Yeah.
Are there further questions for Professor Terrill?
And sure enough, my hands have gone soapy because I picked up the sodium hydroxide.
Sorry, Andrew McKinley. Just a question about the light harvesting. With the chlorophylls they use two wavelengths of light. They use the red and they use the blue. So it slips through, the green slips through.
And that's what you see.
Band from the sun.
Yeah.
I mean, that's an interesting question in itself as to why the green is left out. But from the point of view of the block copolymers, are you looking at harvesting particular wavelengths, or do you tune the polymers?
You can actually tune the polymer to give which one you want.
Right.
And that's the beauty of that system. And it's not even, you haven't got to do the clever chemistry that we talked about with the block copolymers. You don't have to chemically join them together. You've got two, I think they are actually blocks, and you just blend them. So, and blending is literally just stirring them together. It's not even a chemical joining. So as long as you put the right composition in, you get the right colour.
And one last follow-up, okay. Having got these polymers together and they've formed their structure, how do you get the electron out one side and the hole out the other?
For the coloured ones?
Charge separation between, once you've separated the charge, how do you get the charge?
For the photovoltaics, you mean now?
Photovoltaics, yes, sorry.
You literally, that's where the device bit comes in. So you literally do have plates, top and bottom, and you have
Obviously one side has
bias.
to be transparent.
Yeah. One side has to be semi-transparent at the moment. It doesn't have to be fully transparent.
Thank you very much.
Gosh.
Howard Cahoon, University of Reading. To keep your electrons going 99% of the speed of light, what sort of vacuum do you need in that storage ring?
Okay. I think our vacuum group like to liken it to about 500 miles out into space. So it's about 10 to the minus 10 of an atmosphere. The best vacuum pump we have is actually the electrons. We'd actually have to run the ring to get down there. You can only get down so far with the pumping systems we have. And what the electrons then do is actually ionize any final molecules that are left. And then there are, again, charged collector plates where the ions actually go positive and negative, and they're taken away from the cysts of the electrons.
Okay, thanks.
There was a question just behind by the lady.
I wondered what arrangements...
Could you stand up and tell your name?
Groups using the facilities. You're increasing the number of beamlines. Do you have a whole queue of people who want to use these?
Always. I don't think we have a beamline on site that isn't what we call oversubscribed. The way we run most of the beam time for our academic users is a peer review process. So the same way that any academic would go for a grant, and we heard you've managed to get a very good grant recently, they will come and apply to us for a period of days or hours, depending on the beamline, on the system. That will go to a panel of their peers. We don't decide who comes. We provide the technical expertise, And some of us also have some background in the science, so we can collaborate in that way. But we don't choose who comes to Diamond. A peer review panel of academics do that for us. And the facility, the SACS facility, for example, is at the moment about 2.5 times oversubscribed. So we can actually give beam time to a small percentage of the ones we'd like to. We're not saying that the other 1.5 times are not good science, because most of it, actually, the peer review panel would love to give beam time to. So, you know, we're actually turning away very good science because we don't have enough capacity in some respects.
Frank Rossman, one-time materials scientist, now retired.
Can you hold the microphone a bit higher up?
Can you just ask what the background is to the name of the facility?
Our chief exec has a very good answer to that question. Diamonds are hard, and what we do is not exactly easy. And they're also brilliant. And as you've seen, so is our source. So that's where the name came from.
Frank Cotty, ex-GSK, now retired. You mentioned the range of frequencies that were generated by the device. Are you able to tailor those to meet the demands of the experimenters?
Yeah, I didn't describe any of the beamlines we have, but each one will have what we call a monochromator of some sort. If it's a low wavelength, it'll be probably a diffraction grating, a bit like the ones we've actually played with, and that will select out a particular wavelength or a particular energy of light. If it's the X-ray beamlines, we actually use crystals. Most of us actually use silicon crystals, and depending on what angle you have the crystal at, Bragg's law says that you'll get a certain wavelength come off. To make sure that our beamlines don't go miles, we actually put a second crystal in and make sure they go straight on down. So we can actually change this to suit the experiment. And the absorption experiments change that in real time. So they won't actually give the experiment one wavelength of light, they'll actually give it a range of wavelengths, and they'll measure the spectrum in that way.
Are there any further questions for Professor Terrill? Because otherwise I think we should thank again for this really very broad overview, and apparently there's then also coffee and tea available, so where we can meet and discuss further between the audience and of course with our speaker. So let's thank Professor Terrill once more.
Thank you.